Okay, hello everyone. It's awesome to be here. Visiting New Zealand has actually been an ambition of mine for a long, long time, so I'm very grateful for the opportunity to be here and to be with all you folk. So I was, as is the tradition with all speakers everywhere for conferences, I was still working on my slides last night, still working on my talk, and I got it down to about an hour and a half of material. But I figured I had two options. Either I skip every third syllable and trust that you guys are clever enough to put it back together, or I'm going to have to cut some of the talk. So what I'm going to do is I'm going to do things a little bit out of order and skip through all of my first slides and come back to them. Whee! Okay. So part of my talk was meant to be how to become a Python core developer and why you probably don't want to. And we're probably not going to get as far as this in the talk, but I thought the first few slides here are quite interesting, and some people have expressed an interest. So I'm going to do these first, and then I'm going to go right back to the beginning. Okay, so why you might want to be a Python core developer: fame, fortune, and sweet speaking gigs in New Zealand. That turns out to be 1/3 true. Okay. Why you might not want to be a Python core developer. The flames, it hurts. But we're not as bad as the Linux dev mailing list. I assume most of you will have heard of the controversy of, they like to swear at you there. On Python dev, we're just rude to you. We tell you your ideas suck. So if you become a Python core developer, you will be told your ideas suck. You probably won't be sworn at, though. But that's not the main reason not to become a Python core developer. So we're going to look at some of the new things that got added in the most recent versions of Python. And Larry's chuckling down here. His involvement we will learn about shortly. One of the things was adding an enum module to the Python standard library. And the discussions on that thread, I mean, literally ran to thousands of emails. I was interested in this feature. This has come up several times, and the threads have always burned out because just everyone has an opinion. And I burned out after a couple of hundred emails this time, but there were some folk who stuck with it, pushed it through, listened to all of the discussion, and actually managed to come up with a solution that basically, you know you've got a good proposal when everyone's a bit unhappy with it. If you've annoyed everyone slightly, your proposal probably stands a chance of getting in. And that's where we got to, and we actually ended up with it's not all singing, it's not all dancing, but we've got something good that's now in the Python standard library. So other reasons why you might not want to become a Python core developer: you get to write code that people aren't actually going to use for years. You get to write code under crippling backwards compatibility constraints and still be told that you don't care about backwards compatibility. And everything you do will be wrong for somebody somewhere. But the great advantage, the reason why it's a good thing, is you write code, you do stuff that people use. What else did I put here? And you get to give back to Python. You get to help build the future. So it's a great experience. It's something that I can recommend. Really asking, can I become a core developer, is really the wrong question. And I know that's unfair on you because I posed the question, not you. But can you contribute? And we're wanting to make contributing to Python to be as easy as possible, certainly a lot easier than it has. And one of the great tools and resources for that is the core Mentorship mailing list. And this is a mailing list where you can join, you can ask questions about contributing to Python, about fixing bugs, about why no one has looked at your patch in the tracker, and you don't need to don a flame-proof suit before you ask questions. It's a friendly environment, guaranteed friendly environment for asking questions and getting involved with developing Python. So it's on the python.org mail servers, the core mentorship list. If you Google that, you'll find it. And that's a great way to get involved with developing and helping build Python for the future. Right, so let's go right back to the start. Okay, hey everyone, it's great to be here. Thank you for having me as a speaker. at PyCon New Zealand. This is actually my first keynote talk. I've been talking at conferences for quite a while now, spoken at many conferences, but it's my first keynote talk. So I kind of feel the need to justify my presence here, speaking in front of you. And I think it's true to say that I'm the only person who has commit rights to all the major implementations of Python. So CPython itself, I was given commit rights back in 2007. Actually, a bit of trickery and subterfuge there. I was working for a firm called Resolver Systems in London. We were using IronPython. We were one of the first companies to commercially use IronPython. So I, in particular, was very involved in the community, doing a lot of bug reporting. I ended up writing a book on IronPython. And I also happened to, through my involvement in Python, I knew a lot of the Python developers. I actually organized the Python Language Summit in 2007 at PyCon. I think that was the first language summit we had. And we had a discussion, and it was decided that because these are alternative implementations of Python were kind of coming to the fore round about then, that there ought to be somebody from each of these implementations with commit rights to Python who could fix problems in the Python standard library where there were compatibility issues, where the Python standard library didn't work properly with these alternative implementations. There ought to be somebody who could just go and fix it. Now, IronPython at the time was it was a fully Microsoft project, and nobody had commit rights to IronPython except Microsoft developers. But what's more, those Microsoft developers, everything they did was owned by Microsoft. So they couldn't go and contribute anything back to CPython. So me, as a community member, I was originally given commit rights to Python, kind of a proxy for the IronPython project to fix issues there. So that's how I got started with Python core development. That same PyCon, I also started working on unit test, which led to quite a lot of improvements to unit test, which had languished for many years, and the release of unit test 2. So I'm also cheating with Jython. It just so happens that the Jython hosting infrastructure is, they use the core Python hosting infrastructure. So if you have commit rights to Python, you automatically have commit rights to Jython and vice versa. So it's only a social convention that we don't mess with each other's projects. So I've never committed to Jython, but technically I have commit rights. IronPython, as I mentioned, used to be a Microsoft-funded project, as is Microsoft's want. They got bored with dynamic languages, and they defunded IronPython and IronRuby. Having moved some of the core parts, some of the core dynamic features into their .NET framework, which maybe I'll mention in a bit more detail. And about 3 years or so ago, they spun IronPython out as a fully open source project. And because I'd been involved in the community, submitting bug reports and helping fix issues and so on, I was one of the people given initial commit rights to that. Unfortunately, round about the same time, I started working for Canonical. I stopped using IronPython commercially, and I haven't been terribly involved ever since. So that explains how I got commit rights to the first 3 implementations. That just leaves what's probably the most exciting and most interesting implementation of Python out there, which is PiPi. And it turns out it's really easy to get commit rights to PiPi. They sort of give them away with cornflake packets. Because they have this wonderful thing called version control, and they figure if they give you commit rights and you make a nuisance of yourself, they'll just take your commit rights away, and they can just reverse anything you've done. And it turns out that people can basically be trusted, and that people are far more conservative and far more nervous of screwing up than they are interested in wrecking projects. So this is an approach that we're kind of trying to emulate a bit in core Python and be a lot less worried about giving out, a lot less precious, if you like, about giving out commit rights, because it's far more of a danger to us to not have a big enough pool of developers than it is that we let the wrong people in. So I was at a sprint in Lausanne, helping to work on, this was when they were pushing for Python 2.7 compatibility, and I started working pairing with Laura Creighton on the byte array implementation. And if you're not working on the crazy computer science parts of PiPi, the JIT and the JIT generator and the translation toolkit. The PiPi implementation is actually surprisingly accessible to get involved with and start working on. So the RPython is a subset of Python. So the byte array implementation, this sort of core built-in type, is just written in Python. And one thing that they do need to improve, though, is their error reporting. Laura and I had made some changes. It had been reviewed, and I committed it. Because RPython is valid Python, and translation, their version of compiling, takes so long, it takes like 20 minutes to sort of turn the full RPython source code of PiPi into a PiPi executable, you can run all of your tests with Python. Now, that doesn't quite guarantee that everything works, but you do this before committing, and then there's continuous integration. And we committed this change, and then we subsequently broke the build. We'd broken translation. And this obscure error message came out. And it took Armin and Maciek about an hour of poring over the commit logs and the error message to work out how this commit had broken the build. And it was something to do with the way that the PiPi type inferencing reuses functions and compiles multiple versions of functions for the different inputs. And we had an invalid union of types. But I don't think this is something they've improved yet. They need to improve the error reporting of their tools. Starting to work on PiPi is not as intimidating as you might think. Sometimes trying to work things out can be very difficult. OK, so let's... Whoa, what happened there? OK, yes, I forgot what was on my next slide. That's what happened. So why do you care about the different implementations of Python? You're just using Python. Well, it turns out it's possible to write, not just possible, but very easy to write code that is perfectly valid Python code syntactically, but actually makes assumptions about the underlying implementation. And then if somebody else takes your code and runs it on a different implementation of Python, it doesn't behave as you expected, or worse, it doesn't even work at all. And it's useful as a Python developer to have a deeper understanding of which parts of the language I'm using are the specification, Python, the language, and which parts are just implementation details of the way the particular implementation I'm using happens to work, the implementation details. So the very first line there is some code that works fine. If you just want to write some data out to a file, we open the file. We don't keep an explicit reference to the file handle. We just write some data. Now on CPython, because CPython uses reference counting for garbage collection, we don't keep an explicit reference to the file handle around. After we've opened the file handle and written to it, there's nothing keeping it alive. So the reference count drops to 0. It's garbage collected. The file handle is closed. And the data is flushed to disk. None of the other major implementations use reference counting for garbage collection. So what that means is the file handle will be garbage collected at some arbitrary point later. So that data might not be flushed to disk for several seconds. And if this is some test, or you elsewhere in your code assume that that data is already on the disk and read it back in, that code is not going to work. You're making assumptions about you're depending on the reference counting garbage collection implementation. And the next few lines of code, hopefully this is something that if you've been doing Python for any amount of time, that you already know not to do. If you want to build up a string from various bits of input data or source data, don't just increment in a loop. It does work, but it's quadratic in terms of memory use. You create these intermediate strings every time you go through the loop that are then thrown away. Except it turns out that on CPython you don't. There's a hack in the runtime that means this actually performs reasonably well, so that we can avoid a common mistake that newbie makes that causes their code to just run horribly slowly. And what it does is the Python interpreter recognizes that on this plus equals, the reference count of the string is only 1, so you're actually going to be throwing it away after the intermediate string, so it's actually safe for it to build the string up in place. But if you do this, and you run your code on any of the other implementations that can't use this hack, suddenly your code starts running awfully slowly and awfully horribly, consuming vast amounts of memory. We actually, at Resolver Systems, we didn't quite make this mistake, but we did build, well, we made this mistake. It was a bit more hidden. We built up our output file. When saving a file, we built it up in memory by adding together strings on IronPython. So, and it was quite a big method that was called to do this. And IronPython, the .NET framework, wasn't clearing up any of the intermediate strings until we left the method. So not only did we have the output file in memory, but we had the output file in memory effectively hundreds of times due to the intermediate strings not being collected up. And saving a file could blow up and die with out-of-memory errors. So it's surprisingly easy to make this mistake, even if you don't recognize it. OK, so let's look at the individual implementations. This is a horrible pun. There's no such thing as a CPython. That's just a sea snake. OK. So CPython is almost certainly the version of Python that you're using. Hopefully, you're able to use Python 2.7, and maybe you're able to use Python 3. As is obligatory at conferences, somebody has to ask, how many of you have got to use Python 3 in production for some production code? OK, there's a few hands. That's great. How many of you have written some Python 3 compatible code? A lot more hands go up. That's great to see. That's really good. Python 3 is a much nicer language to use. Alex Gaynor, a prominent Python developer these days, still a young guy, he said Python 2 is the next COBOL. People are going to be paid to maintain Python 2 code for years and years to come. So there's good work for you all out there in the next couple of decades, maintaining horrible legacy systems in Python 2. So one of the things when Python 3 was, the efforts were seriously underway to get Python 3 out there, the Python core development team, we all thought that the 2 to 3 tool, or maybe its inverse, 3 to 2, was how people were going to develop projects and maintain projects that were compatible with both Python 2 and Python 3. That you'd have a single source code base, either in Python 2 or in Python 3, and then you would use a translation tool that would then generate the, say if you're using 2 to 3, you'd have a Python 2 code base, and you'd use the tool 2 to 3, which would generate your Python 3 version. And you'd then run your tests. And if there were any breakages, any tests that failed in Python 3, you'd actually fix those in your Python 2 version. So you could maintain a single code base, but have both versions available. It turned out that that's not a nice way to develop. And the big problem is, particularly if you're using 2 to 3, is you have a Python 2 code base, but people can't provide patches against the Python 3 version, because you're only maintaining the Python 2 version. So what it turns out that most people have done is actually develop a single code base. Nobody really wants to maintain 2 versions of their projects and have to keep them both up to date in parallel, but write in kind of a subset of your code that is compatible with both Python 2 and Python 3, and use libraries like SIX, SIX, a project by Benjamin Peterson, which provides a compatibility layer. So all of the things that have, well, a lot of the things that have changed between the 2 versions of Python, SIX provides a sort of single point of contact where if you use them from SIX, it's the same for both versions. So it does a lot of the work for you in terms of compatibility. This approach still kind of sucks, because Python 3 is a great language. Python 2 is a pretty good programming language. But the subset of Python that is compatible with both Python 2 and Python 3 is worse than either of them. So it kind of sucks, but it works, and you have a single code base you can maintain. And you only really have to do this for your library code that other people will use. Your application code, you're typically targeting a specific version of Python. So this is the approach we're seeing most people use, most projects use for Python 3 compatibility. And the big reason that people have not switched has always been the dependencies. I can't switch to Python 3 because Django isn't there. Django has finally fallen. Django now has Python 3 support, and projects like Twisted and NumPy are still working on it. But the number of projects that support Python 3 is increasing sort of almost every day. Okay, this is a horrible, horrible photo. This is from 2007. This is actually the IronPython team and community. It's very blurred. You can see me there without beard. There's looking very scary. Thankfully, it's blurred enough that you can't see how scary I am. There's a sad story behind why I had no beard at this point. This is the first PyCon I attended in Dallas, and it was my first visit to the United States as well. And it was really important to me that, look, I'm going to get into America and attend this conference. And I'd heard all sorts of scary stories about the TSA. And this PyCon in 2007 was in Dallas, in Texas. And I thought, they really don't like hippies in Texas, do they? So me there with my scruffy beard and scruffy hair, looking like a hippie, they're going to kick me out on first sight. So I thought, well, I'll shave the beard. I'll look a little bit smarter. And actually, I've since been to America quite a number of times. The Dallas airport was actually my nicest experience of getting into PyCon. And I didn't see a single gun in my whole visit to Texas. I was very disappointed. So from the left to right on that picture, there's Dino Wieland, who at the time was a team member, went on to become the team lead for IronPython 2, and now is working on Python tools for Visual Studio. So Microsoft Visual Studio, their premier IDE, has pretty good support for both CPython and IronPython and things like IPython as well, built into it, and largely the work of this guy. The next one is Jim Hugenin, who's the creator of IronPython, and also the original creator of Jython, and also the original creator of NumPy. So a pretty important guy in terms of the history of Python. And then there's Sarah Sangyeon, who was a community member, this genius Korean guy, and Mahesh, who was the IronPython program manager, myself and a colleague. Lovely guy, Andrzej Schufter, a Polish developer, unfortunately an unredeemable Ruby enthusiast. So, okay, so where's IronPython at? IronPython, they have a version of Python 2.7 out, IronPython 2.7, and they have a beta of 2.74, so they're working towards a 2.74 final, which will probably be the final release in their 2.7 series, and they're switching to, they have some Python 3 support, they're switching to fully working on Python 3. Jeff Hardy, who is now the main developer of IronPython, has this wish list of things that he wants to work on next. That and the test runner only works on Windows. It was inherited from the original Microsoft project and really needs sorting out. Why would you use IronPython? So IronPython is an implementation of Python for the Microsoft .NET framework. It also runs on Mono, so technically it's cross-platform. Whether you accept that or not depends on how much you like or dislike Mono, I guess. People tend to have very strong opinions on the topic. It's written in C#, which is Microsoft's statically typed copy of Java. They learned from Java's mistakes, so it sucks a bit less than Java in some ways, but sucks differently in new and exciting ways instead. I actually quite like C#, Resolver Systems. I did a bit. As statically typed languages go, it's not bad. One of the things that Jim Hugenin did, having developed IronPython, the first version, is they then took kind of like, if you like, the dynamic parts of out of IronPython and created this thing called the dynamic language runtime, and the core bits of that are now built in to the .NET framework. So it was designed around a statically typed system, but in C#, you can statically declare that an object is dynamic. And what that means is that member lookups and operations on that object will be done at runtime, as we expect, so full dynamic goodness, and done by the dynamic language runtime. And one of the core use cases for that is that means that from a C# .NET application, interacting with objects created from IronPython is surprisingly easy. You just say, hey, this stuff is dynamic. Why you might want to use this? Well, typically, the reason for using IronPython is, well, we're using .NET anyway. I'm stuck on the .NET ecosystem, so I might as well get to use Python. But there may be some framework, tool, or library that you just need to use from the .NET framework, and IronPython is a great way of accessing it and experimenting. And there are some really great features in the .NET framework. It doesn't use reference counting for garbage collection, which means we can get away without having a global interpreter lock. You can use multiple cores on your system. And there are features like app domains in the .NET framework, which we don't really have an equivalent for in Python. So those are the typical reasons you might use IronPython. Then there's the equivalent for the JVM ecosystem, the Java Virtual Machine, and that, of course, is Jython. When I say a small team hindering development, I mean the fact that it's small is hindering development. Not that they're actively hindering the development. Okay. You're very kind, thank you. So they're a little bit behind IronPython. They're still working on the Python 2.7 support, and they don't yet have Python 3. Their big plans are for Python 3 after they get Python 2.7 out and released, which shouldn't be too long, I'm told. The reasons for using Jython are pretty similar for the reasons for using IronPython, except transfer to the JVM. If you're on the Java Virtual Machine already, if you've bought into that ecosystem, then you might as well use Python and use Jython. Jython's been around longer, so it probably has more users than IronPython. And it's improved a great deal recently, and also has no global interpreter lock. So the last and most exciting implementation of Python is PiPi. And that does have a global interpreter lock, I'm afraid. So you can't, with vanilla PiPi, you can't use multiple cores out of the box without using multiple processes. PiPi has lots of other exciting things, though. One of the most exciting things was they just announced a beta of their Python 3 support, targeting Python 3.2, which is great. They also have NumPyPy, which is their port of the core parts of NumPy. Now, the reason this makes sense for the PiPi project is PiPi has a just-in-time compiler, and one of the things it's very good at speeding up is numeric operations. PiPi can increment a number a zillion times faster than CPython can. But what that means is that the core set of people who are interested in using PiPi are very similar to the core set of people who are interested in using NumPy. And they typically want a richer array type than the built-in types in Python provide. So porting across NumPy makes a lot of sense for the PiPi guys. Now, PiPi still seems to cause a bit of confusion amongst the Python community, maybe because they've not done a wonderful job. They're all computer geniuses and not necessarily the best at communicating, although they've made a tremendous effort in terms of their blogs and so on. And maybe just because it's a bit unfortunate that the whole project is named PiPi. PiPi meaning Python in Python. PiPi is actually two projects. It's a translation toolkit which takes a program written in RPython, and translation effectively means compilation, but in a weird and complicated way, and turns it into an executable, or in theory, something that runs on the JVM, or something that runs on the .NET framework. They've never had that running particularly successfully, but just about every bit of the translation toolchain is pluggable. It can also compile in a just-in-time compiler. We can add things like software transactional memory, greenlet, stackless operation. Stackless operation is built into PiPi now and is now integrated with the JIT, I believe. So it's another reason why PiPi is interesting and exciting. So that's the translation toolkit. Alongside that, they have an implementation of the Python interpreter that is written in RPython, this static restricted subset of the Python programming language, and you feed that to the translation toolkit, and it spits out this native executable. So the version of Python that's written in Python is the implementation of the Python interpreter that's written in RPython, and that's what the translation toolkit takes this and creates the PiPi executable. So those are the two aspects of the PiPi project. PiPi has fantastic, probably the best compatibility with CPython in terms of the semantics and the language of all the implementation. It diverges the least. The reason you might have difficulty porting your code to use it is because it although they have a sort of a compatibility layer for the Python C API, not all C extensions are supported. So if your code uses C extensions, you either need to replace it with something that works on PiPi or report bugs to the PiPi guys until they get it working. One of the really exciting things that's happening with PiPi, though, at the moment is the software transactional memory, and this is PiPi's plan for getting rid of the global interpreter lock. The global interpreter lock is what means that only one thread of pure Python code is active at the same time, even if you have multiple threads running. In Python, multiple threads, there'll be real OS-level threads. It's not what's called green threading, but still, due to the global interpreter lock, only one of them will be active at a time. Unless you drop into C code that releases the global interpreter lock. PiPi's plan to get rid of this is not to add all the fine-grained locking to the interpreter that would then slow down the interpreter and have this huge performance penalty, but instead to use something called software transactional memory. And this executes your code in a transaction, a bit like a database transaction, the same term. It automatically works out where to put these transactions around side effects. Because what happens is it executes the code in the transaction. If nothing else, no other thread touches the objects in that transaction is then committed and succeeds. If something else touches the same objects or changes the same objects during that transaction, then the transaction is restarted. And this is what I mean by the transactions are inserted around side effects. Obviously, something that has side effects like writing to disk can't just be re-executed. So the PiPi implementation of STM works out how to divide up your program into these transactions. And using STM, they can actually guarantee that the results will be correct, as if you'd had the right fine-grained locking in place. Obviously, you may still need your own locking around shared resources. But that's a very interesting approach. They have it working. It doesn't yet work properly with the GIL, with the JIT, for complicated reasons. But essentially, the core of it is that the JIT generates machine code. That's the job of the JIT. And it hard codes the address of objects. And when you're inside a transaction, you need to be working with a copy of the object. So if you then drop into machine code that hard codes a reference to the wrong object, that's not fully working. So there are difficult problems for them to solve, but Armin's the guy to solve them, and it may yet solve us from the global interpreter lock. So PiPi, very exciting, usable now, in use, in production use, in quite a few places, but certainly nowhere near as used as CPython. Okay, what next? Okay, so Larry Hastings is here. Do you want to stand up, Larry? Larry is the release manager for Python 3.4. So if Python 3.4 sucks, it will be this man's fault. Not true, not true. And Python 3.4 will not suck. So let's have a look at what's really new, the very new in CPython. I have no idea what time it is, which is good for me, maybe not so good for you. I'm just going to keep going until somebody waves at me. Somebody at the front. I don't accept arbitrary waves. So these are the PEPs that are currently accepted for Python 3.4. And I'm going to look at these. We're going to go through these very quickly. So by it's complicated, what I mean is these PEPs have fairly specialized use cases. So either you will know and understand what they're all about, or they're probably not very interesting to you. PEP 446, making file descriptors non-inheritable by default. This affects subprocesses and fork. At the moment, file descriptors are inheritable by default. This is a cause of certain security issues and some OS-level race conditions that can't be fixed except by making them non-inheritable. And then there are new APIs for creating inheritable file descriptors. So it is a backwards compatibility issue, but it's also a very positive change forward and a lot of work by Victor Stinner, I think, to get that done. Type.local lookup, added because the Python object model just wasn't complicated enough already. And PEP 442, a little bit under the hood, cena object finalization, probably not something you need to know a great deal about. It's particularly for objects that take part in reference cycles. The work here was done, the specification and the actual work was done by Antoine Pitrou, and improves the garbage collection. There are now less cases where objects can't be garbage collected. So that's a nice change, but a bit under the hood, if you like. So these two PEPs are interesting, but not really a very big deal. Configurable memory allocators, that's a big deal if you embed CPython and you want to be able to control the way that memory is allocated. Before, you would basically have had to patch CPython and maintain your own version to do that, whereas there are now C-level APIs for doing this. Another really interesting use case for this, though, is you can switch in a memory allocator that deterministically and in a controlled way fails to allocate memory and therefore causes out-of-memory errors to be raised. And you can test your application's handling of low memory situations. Because that's notoriously difficult to test, most applications that attempt to handle low memory situations do it badly. If you don't test it, it's broken. If you do test it, it may not be broken, is generally the rule. PEP 435, enums, I mentioned them briefly already. Great, finally, an implementation of enum in the Python standard library with sane semantics, with a class-based API and a kind of functional API similar to named tuple, but done through calling the class. There's also a backport of this up on PyPi. So if you want to use enums in your application, you can use the enum project and you get the same API as will be in the Python standard library. It doesn't yet have flaggable or flag enums that you can OR together, but that's something that can be added at a future point. It was decided not to try and do everything, because even this took thousands of emails to get there. And the main benefit is you get groups of named constants, and those named constants have a sane and useful repra. So when you're debugging, you can see where these values came from, and you don't just have random arbitrary integers sort of floating around your data structures. Now, my understanding of this PEP is that it's been basically approved by Guido, but hasn't yet been implemented, reading through the discussions on Python Dev.
I think so.
I really like it. Python 3 already offers some extended unpacking syntax, and this just relaxes the syntax a bit further. And you can see a consequence of that in the very bottom line is there's one obvious way to do it for unpacking arbitrary iterables into a single flattening nested lists, for example. This is nice. This subtests and unit tests, again, something done by Antoine Pitrou. There wasn't a PEP for it. It's really quite a small feature, but it's a lovely little detail. This is an alternative to test parameterization, which is something that test frameworks like Nose and Py.test both provide. If you have a bunch of related conditions that you want to test in unit tests, a common way is just to do it in a loop. But what that means is that unit test will stop on the first failure. You might have several failures, and what you've got to do at the moment is it will report the first failure, you fix that, then it reports the next one. And also, the failure message might not be very useful. It might say, this test assert x equals y failed, but it doesn't tell you the useful information about under what conditions it failed. And if it's inside this loop, that might be crucial information to help you fix it, and you've then got to go back and add print statements or build up a more complex error message. You can see we've got quite a nice API here using the with self.subtests, and we tell the subtests context manager what's the interesting information about this loop. And you can see that the failure message then includes that information in the report. So a nice, useful little feature. There are lots of other details in Python 3.4 already. We're only at the Alpha 1 stage, so there's still... When's the final release roughly scheduled for, Larry?
Final release is about, I think, it's 4 or 6 weeks before PyCon US 2014.
Right.
So we can slip a whole bunch and still hit it before PyCon.
So about sort of March 2014,
yeah,
that kind of time.
It's late February, early March, I think.
Right, right.
And by the way, just in case this is interesting, I'm going to cut Alpha 2 here in New Zealand. I'm going to tag it tonight and hopefully release it tomorrow while I'm still here.
Okay, so we get a Kiwi Python 3.4 Alpha 2. And I'm glad he's doing that tomorrow, not yesterday, so my slides wouldn't be out of date about the Alpha 1. I'm very grateful, thank you.
Well, the time thing.
You mean it might have happened yesterday already? Okay, so stuff that's still to come. Oh yes, I was just saying there are lots of other interesting details, like, for example, the UTF-32 decoder got about 4 times faster. Set object hash collisions got about 20% less expensive due to taking advantage of cache locality. So lots of nice little details in Python 3.4. And some stuff that's still to come. PEP 436, the argument clinic. That's one of Larry's PEPs, mostly about making it nicer and saner for writing C code. But one of the nice side effects of this is it might be able to automatically add signature objects to functions and methods written in C. I don't think that part is finalized, but I'm looking forward to that bit being done, because that will mean that the inspect tools, like inspect.getFullArgSpec, will finally be able to get useful information out of the built-in types and stuff implemented in C. So that will be a really nice side effect to come out of PEP 436 when we get there. PEP 453 is interesting because this is adding, the Python dev team have decided to bless pip as the official tool for installing Python packages, but we are not moving pip into the Python standard library. What we are going to do, probably, is add a bootstrapping module that will come with the Python installer and will then install pip and all its dependencies for you if you want it. And the interesting thing is this PEP talks about not just adding this to Python 3.4, but also adding it to earlier versions of Python that is still under maintenance, which includes Python 2.7. So I hope we do this. Tulip is a very interesting project by a certain gentleman called Guido van Rossum, which is an async library and framework. He has said he will put it in the standard library. It is under active development. He hasn't promised it'll be done in time for Python 3.4. It's under very active development, so it'll be interesting to see whether or not that happens. But this is an async network framework currently being worked on by Guido and a whole team of other people who have got involved. Okay, stuff that's already in Python that you may not be aware of. I'm sure you've already seen these HTTP status cats, so I thought you'd probably seen the 404 one, I preferred the picture for 405. So I just put the 405 one. PEP 404 talks about what will happen with Python 2.8. There will not be a Python 2.8, I'm sorry to say. I have 5 minutes, so I'm going to have to start skipping syllables. Okay, stuff that's in Python 3 that you may or may not be aware of. So this is not the difference between Python 2.7 and Python 3 is huge, massive list. I'm not going to go through it all. So really, this is stuff that has happened since Python 2.7. That means 3.2 was about the same time. So this really means stuff that's in Python 3.3, except for the new GIL that was in Python 3.2. It turns out that the global interpreter lock in Python 2.7 thrashes when you have multiple cores because the OS tries to wake up the threads that don't have the lock. That was fixed in Python 3.2. We still have a global interpreter lock, but it doesn't thrash so much. Flexible string representation, no more UCS2 and UCS4 builds of Python. If you understand what that means, it's a big deal. You don't have to compile the right version of an extension for the wide or the narrow build of Python. And if you have 8-bit Unicode strings, they no longer take up 4 bytes in memory each because we have an internal 4-byte representation. Now, if you have ASCII or Latin 1 strings, the internal Unicode representation will be 8-bit. So Python, under the hood, will pick the most memory-efficient representation, which is also likely to be the representation you're encoding to. So it also massively improves the performance of a lot of encoding operations. A key sharing dictionary, reducing the space taken up by object dictionaries. By most object instances have a dictionary storing the attributes. Most of them have the same key set. So storing the set of keys in every single instance dictionary was a huge waste of space. And this was implemented by Mark Shannon. He reckons by his benchmarks, saving about 10 to 20% of memory on a typical application due to this optimization. And a C implementation of decimal in Python 3.3 runs hundreds of times faster than the pure Python implementation, even outperforming float in some instances, mainly in getting the string representation, because getting a string representation of floating point numbers is actually a surprisingly hard computer science problem. And there are all sorts of standard algorithms for how do you turn an IEEE float into a string representation. Mind-bogglingly complex stuff. But the C implementation of decimal is great, and really, all of you here ought to be, you need to be aware of Unicode, and you need to be aware of the problems with floating point numbers, and when and why you should be using decimals instead. And now using decimals is viable. They're not such a huge performance hit. Okay, some huge changes, and I really don't have time to go into all of these, which is a great shame. .pyc files are dead, sort of. They now live in a dunder PyCache directory, so they don't clutter up your source tree. And this is something that just about every Python developer has at some point. You ever had the experience where you delete a Python file, and then your code does really odd things because it's somehow importing from a stray PYC file that didn't get deleted? That no longer happens. If the Python file is gone, then the .pyc file in the dunder PyCache directory won't be imported from. You can still do .pyc file only distribution if you really want to, God help you. But by default, you don't need to see the compiled bytecode anymore. Dunder init.py files are no longer needed. PEP 420 namespace packages. You can have namespace packages that can be extended from different locations on sys.path, and you don't need to use a dunder init.py. A big change for Python. PEP 3150, PEP 405, virtualenv, or all the interesting bits of virtualenv anyway, now built into Python through the VM module. PEP 3151, more work by Antoine Pitrou, not changing all exceptions, but reworking the OS error and the IO error exception hierarchy, making it cena, and more fine-grained. There shouldn't be any reason to need to check the error number attribute of exceptions anymore. You should have specific exceptions instead. And the Python launcher for Windows is great. Finally, the Python Windows installers puts Python on the path after installation. So you can install Python, go to the command line and type Python, and something happens. But the Python launcher is also interesting, is also available as a separate download, and makes working with multiple versions of Python on Windows more pleasant. Through the command line, you can then specify, run this script with this version of Python. But more interestingly, if you don't specify a version, it will read the shebang line and use the correct version of Python. So effectively adding what Linux and Unix have had for decades. More or less. You could use the Python launcher for launching Perl scripts if you wanted. Highly not recommended, but possible. New modules. Fault Handler generates Python exceptions on segmentation faults and is available on PiPi for Python 2.7. Very useful, particularly if you're working with C extensions. Unittest.mock is awesome. Rocks. IP address does pretty much what you would expect. A library for working with network objects, LZMA, and new compression formats. Lots of interesting little details. List.copy is another. Finally, there's one obvious way. There are lots of ways to copy a list, and now there's one obvious way to do it. Contextlib.exitStack. This replaces the deprecated and broken contextlib.nested and is a really nice, powerful feature. Don't have time to go into it, but it's also the need for this is a very good example of why only providing a context manager as your API to certain functionality is a bad idea. If you have functionality for which a context manager is suitable, yes, please give me a context manager. Context managers rock. But don't let it be the only way that I can get this functionality. Because then I have to start doing things like calling dunder enter and dunder exit manually in my code. And that's really horrible. But if you have to do this, like work with dynamic lists of context managers, contextlib.exitStack is now available. Simple namespace. There's probably a version of this in every major project out there. There's now one in the Python standard library. A new attribute on methods and functions, giving you the full path to finding them. Huge changes in the packaging world. You can read this for yourself. Bundling get pip, that's PEP 435 that I mentioned. Wheels is an entirely new binary installer format. This was always the big problem with pip. It couldn't install binaries, which meant if you were on Windows, you probably couldn't use it because you probably didn't have a compiler. And if you're on Mac, you might not have a compiler available. PiPi has a content distribution network, so the mirroring auto-discovery and naming system is now obsolete. The good news, though, is that even though distutils 2 is dead, distutils 2 had this change-the-world approach to solving the problems with Python packaging, and it ultimately failed because the developers burnt out. But the work is not being wasted. It's now being picked up again by quite a team of people. I think they're much more likely to succeed, and being done piecemeal. There's a bunch of PEPs around it, PEP 426 being one of those, so well worth looking at. And there's something called distlib, which picks that up and is, again, available for earlier versions of Python. There's lots of other exciting changes in the Python world. I think I'm pretty much exactly out of time, so this list will have to stand. I'm hoping that we'll hear more about the PSF, the Python Software Foundation. It's going to be much easier to join the PSF, much easier to get involved. And OpenStack, I think, is a big deal for the Python world. So I think I'm going to draw it to a close by saying, should you get involved? Yes. And in October, I am doing a parachute jump for charity. Please sponsor my parachute jump. This is for the Big Issue Foundation. Thank you very much.